So we're looking at the difference quotient and looking at the definition of a derivative of a function and of a derivative at a point. And we looked at the difference quotient in the last class period. And we actually talked about this and I showed this, so this is just a quick review. But that difference quotient, this was in the form of x plus h minus f of x all over h. And that was actually, we looked at it, we had a graph. Come on. And basically took something here, which was x, so took something here, which we just added h to it, had 2 points on the line or on the function. This here was f of x plus h, so the y value, oops, that was actually just f of x. Down here was f of x plus h. So all this was the slope between these 2 points. And so our slope is equal to the change in our y value. So f of x plus h minus the f of x value all over the change in our y value. So x plus h minus x. And we see that that gives us our difference quotient here because in the denominator, that h cancels. I'm sorry, the h doesn't cancel, the x cancels, leaving you with just the h. So if we joined these 2 points, the line that joins them is called the secant line. And so you just found the slope of the secant line using this. We also say that between those 2 points, we're looking at the average rate of change of what's going on between here, taking the average of those values. If we're talking about position of something and moving it, this could be the average velocity or average speed, average rate of change in cost or revenue of a profit. So if we took this h value and we shrunk it down, we made this h value go towards 0 and get very, very small. And this is where we were looking at limits before in the past. This gives us the slope of the tangent line. So if we were looking at the graph and we wanted the slope of a tangent line, basically you're making, again, that value of h go to 0. And so when that goes to 0, we can see what's more accurately going on at this value. And so the line that touches the point and has the exact slope, or rate of change right there at that point, is the slope of our tangent line. And this line here is our tangent line. We say that that's the instantaneous rate of change or instantaneous velocity, or the marginal cost, revenue, or profit. Okay. So this was just an alternate form of the derivative. I didn't use that form. I tend to like the other one, but if you want to, you're welcome to use that. Okay, so let's pull some examples. So that was just like a quick review, unless you have any questions on that. So at the end of class period, the other day, we looked at an equation where we had y was equal to some constant k. And I said, okay, well, if you have y equals a constant k, that was just a horizontal line through k. Pretend that's horizontal. And if we look at a slope here, your y value is always the same. And so our slope of a horizontal line is 0. If they ask us to graph the derivative of y. The derivative function. Of y equals k. Well, basically the derivative function, every point on there, it's the same x values we have here, but this would be, let me call this f of x. Just makes life easier sometimes. This would be f prime, and let's say this is x0 of x of 0. Okay, so those are where our points are. Well, if I take this point right here, x of 0, and I find the slope right at this point, it's going to be 0. My slope is 0, always on that horizontal line. And so if I took 1 and I plotted 1, my slope is still 0. And so here are my points on y prime of x, or y prime. So if I had x equals 0, my slope is still 0. If I had x equals -1, my slope is still 0. So I'm again getting a horizontal line, but this horizontal line is on the x-axis. So any number I plug in here, I get back 0 for y. And so if I plotted y prime, this would just be a horizontal line. Pretend that's horizontal and that's lying on the x-axis. There we go. This would be y prime, which is the same thing as writing f prime of x. So some other ideas, because you're going to be looking at a function or a graph and then going backwards and trying to graph that derivative. So let's just start with the easier ideas just to get that concept kind of down. So if we had just a function, let's say f of x is equal to -x. So hopefully you can look at this equation and tell what the slope is right away. This is in the form of y equals mx plus b. It's a line, right? And in here I can see that my slope here is -1. If we want to think of it, -1 as a rational number, we can write this as -1 over 1, or we can rewrite this as 1 over -1. If I was just to graph y equals -x, so when x is 0, -0 is 0. When x is 1, y is -1. Just plotting points. X is 2, plug it in, you get -2. If I plug in -1, negative of -1 gives me 1. So I have this line here. And this is f of x equals -x. So from here, we should also be able to, let's graph f prime of x. So every point that's here, so when x is 0, we have to look at what is that slope. So this would be the slope of f of x at x equals 0. because this is a line, it always has the same exact slope, any point on that line. And in our case, that slope is going to be -1. And so here then, if I start thinking of my points, I'm going to have one at 0, -1. Let me just plot that. Actually, let me get rid of that other, oops, I can't. Just so we didn't get confused. Okay, so we have one at 0, -1. So when x is +1, my slope is still -1. Oops. And then when my point is 2, my slope is still -1. Here at -1, my slope is still -1. So I notice that I'm getting this points of my f prime of x are giving me a horizontal line. So this would be f prime of x, which equals -1. Okay, so I saw that without going through and having to use the definition of the derivative and the limit, just by knowing that information about a line. A line always has a slope. When it's in this form, y equals mx plus b, the coefficient in front of x. So you should be able to, and we could do it really quickly, take the limit of that and show that. So let's find f prime of x by using the formal definition of a derivative. So soon, hopefully next week, we're going to look at a different way to find the derivative, which is a lot easier than doing this limit. Oops, of the derivative. Which again is the limit as h is approaching 0 of f of x plus h minus f of x all over h. So limit as h goes to 0. Well, our f of x was just equal to -x. So our f of x plus h, so if we go in here and plug in x plus h, wherever we see an x here, we get this is equal to negative. Then plug in x plus h because there's the x. And then minus f of x. So minus this function, which is -x. We put this all over h. So if we distribute that negative and rewrite this, we have the limit as h goes to 0 of -x minus h plus x, because minus a negative is positive, all over h. So notice those x terms cancel out in the numerator. -x plus x is 0. So we have a limit as h goes to 0 of -h over h, which both simplify down. We can cancel the h, leaving us with the limit as h goes to 0 of -1. Oops, I don't want negative. And we said the limit of a constant is always equal to that constant, so it's -1. Okay, so it just showed it using the formal definition, just to kind of give us a quick review. So graphing the derivative, we're going to look a little more of that in this next section, which I'll hopefully get to more today. But let's go back to finding some equations, and a little more difficult than a linear, or we looked at a quadratic on Monday. So let's say we have f of x is equal to -3 all over x plus 1. So for each function, find the equation of the secant line through the point where x is given, and B, find the equation of the tangent line when x has the first point. Okay. So A, we want to find the equation of the tangent, or sorry, find the equation of the secant line. Through x equals 1 and x equals 5. Okay, so we need to look at points. We need to find our points when x is 1, and we need to find our point when x is 5. So when x equals 1, so we're just going to go back in here, we're going to plug in 1 wherever we see an x in f of x. So this gives us -3 all over, I see an x here, so I'm going to replace it with 1 plus 1. So let's reduce. So we have -3 all over 1 plus 1, which is 2. So we know we have a point on the graph and the point on the secant line at 1, -3/2. So let's find the point when x is 5. So now we're going into our function f of x, and wherever we see an x, we're going to replace it with 5. So we have -3 all over x, which is 5, plus 1. So we have -3 all over 6, which reduces to -1/2. So we have a point when x is 5, y is -1/2. So we need, in order to find the equation of a line, we need a point. Now we have 2 of them, and we need a slope. We don't have the slope, but we can find the slope between 2 points. So our slope is equal to the change in our y value, so -3/2 minus this other y value, which is -1/2, all over the change in my x value. I started with -3/2 point on the top, so I have to start with 1 for my x value in the denominator, so 1 minus 5. But minus and negative is really addition. We already have a common denominator in that numerator, and so we get -3/2 plus 1/2. Adding fractions, you add the numerator, keep the denominator the same. You can only add them if they have a common denominator. So -3 plus 1 is -2 all over 2. And this is all over 1 minus 5, which is -4. But notice my numerator, this -2 over 2 reduces to -1. So we have, this is equal to -1 over -4. So we get that m is equal to 1/4. Okay, so it didn't want just this, it didn't want the slope, it wanted the equation of the secant line. So now with that, we can find the equation of the secant line. I know that your book does it a little differently than I do it. They use the point slope formula, y minus y sub 0 is equal to m times x minus x sub 0. They might write it a little differently if y is, it's just another way to say our function f of x. So f of x minus f of x naught is equal to, well, our slope is actually equal to the derivative of our function. So f prime of x sub 0 all times x minus x sub 0. So you might see this in the book. So this is equation of a line. Of the secant. Actually, this would be the equation because I'm looking at the derivative. Let's do that different. This is the equation of the tangent line. Which is not what we're looking at right now. We're looking at the equation of the secant line. So,
Professor,
mm-hmm.
Did you say that both of those equations are the same thing, the y minus y0 and the f of x down there, like they're both the same?
Yep.
Okay.
Yeah, so it's just different notation. And so instead of writing our point as x and y and x sub 0 and y sub 0, they're just using function notation. So this would be x, f of x for y, and this would be x sub 0 and then f of x sub 0 for y. And so just replacing those values, so y is f of x and y sub 0 is f of x sub 0. So the equation of the secant line, we needed the point and we needed the slope. And we have both, and it doesn't matter which point you choose. So we can choose 1 and negative 3/2, or we can choose 5 and negative 1/2. And in the end, we would get the same equation because they go through both of those points. And so the secant line, maybe we'll just go through it one time this way. We have y minus our y value of our point. So if I'm using that second point, that y value is negative 1/2. So minus 1/2 is equal to our slope. Well, our slope we saw was positive 1/4. All times the quantity x minus our x value of our point. And our x value of this point is 5. So if we clean it up, minus a negative is really positive. So we get y plus 1/2 is equal to, we can distribute this 1/4. So 1/4 x. That's a positive 1/4. 1/4 x minus 1/4 times 5. So this is minus 5/4. Get x by, or y by itself, you could subtract 1/2 on both sides. But I notice when I subtract it from my constant of negative 5/4, I'm going to need a common denominator. So let's, at this point, let's just get a common denominator right here. So let's multiply the negative 1/2 by 2/2. So bringing our y down, we get, this is equal to 1/4 x. And then a negative 5/4 minus a 2/4. So negative and a negative adding. So this would also be negative. So 5 plus 4, I'm sorry. Negative 5/4 minus 2/4. So that's negative. So minus 7/4. Okay, so we just found the equation of that tangent line. Not the tangent line. Sorry, I keep on saying that. The secant line. Okay, so the next part was to find the equation of the tangent line going through the first point. And so our first point that they asked us, our first x value was 1. Okay, so we're going to go part B. And the equation of the tangent line. Of f of x equals negative 3 all over x plus 1 at x equals 1. Okay, so we need a point, but we already found that point. So when we plugged in 1 in for x, we got negative 3/2 back for y. So we got our point. Now we need to find our slope at a particular value on our function. And so we can look at the limit as h approaches 0 of f of x naught, which is 1 in our case, plus h, minus f of x naught, which is 1 in our case, all over h. So we got to go back into our function, and wherever we see an x, we're first going to go in and we're going to rewrite it with 1 plus h. So wherever we see an x here, rewriting it with 1 plus h. So we have negative 3 all over, I see the x there, so I'm replacing it with 1 plus h. And then outside of the x, I have a plus 1 in the denominator. And then it tells me to subtract off f of 1, so minus, so I'm just going to go back in here, wherever I see an x, I'm plugging in 1. We actually figured out what that number is already. So negative 3 all over x, which is 1, plus 1. And we put this whole thing all over h. So simplifying, we'll notice that you're going to get h over 8. I'm sorry, you're going to get 0 over 0. Because our first fraction in the numerator, we have negative 3 all over 1 plus 1 in the denominator, which is 2 plus h. Again, minus a negative tells us we're doing addition. So plus, and then I have 3 all over 2. And this is all over h. So notice as your h value is approaching 0, we can say that this is the same thing as saying negative 3/2 plus 3/2. which is 0, all over 0. Okay, so some of you on that one in class exercise, we're stopping there at that 0 over 0, but that actually doesn't tell us anything about the limit, and we actually have to go back in and manipulate it. So indeterminate form. So we're not done, we got to go manipulate it. So let's go back to where we had simplified it. So if we looked at the limit as h goes to 0 of -3 all over 2 plus h plus 3/2 all over h. So there's different tricks. If this was a rational function, so you had a polynomial divided by a polynomial, and you got 0 over 0, your trick is to factor. In this case, I notice I have a complex fraction. And so the trick, if you get 0 over 0 there, is to get rid of the complex fraction. So we want to manipulate this so it's just a single fraction. It's not fractions within fractions. And so there's two different methods of simplifying when you have fractions within fractions. I personally like the method where I multiply both the numerator and denominator by the LCD of all the fractions within the main fraction. So if I look at these two fractions here, -3 over 2 plus h, and I look at the fraction 3 over 2, my LCD of these two fractions, unfortunately, even though they both have a 2 in it, that is not a factor of this 2 plus h. So our LCD is going to be each denominator. So 2 plus h all times 2. So if I multiply by that fancy one of that LCD, I'm just going to write the 2 first if that's okay. So 2 times 2 plus h all over 2 times 2 plus h. But the whole point of that was when I distribute that to the numerator, I chose something that would cancel out with my denominator. So we really have -3 all over 2 plus h. Distributing, that would be, this would be 2 all times 2 plus h. And we have plus 3/2. But we have to distribute this 2 times 2 plus h over here too. So 2 times 2 plus h all over our denominator of h times 2 times 2 plus h. It just disappeared. If it helps you to see that as 2 times 2 plus h over 1, you can write it like that. But the whole point again was so that these factors, these would cancel out. And so we are only left in the numerator. So we have the limit as h goes to 0. So I have a -3 here, all times this 2 here. So this would be -6. Plus, so the 2's cancel. Let's distribute the 3 inside the 2 plus h. So 3 times 2 is plus 6, and 3 times h, so plus 3h. All over 2h, all times 2 plus h. I don't want to distribute this denominator. If I do, it's just harder to see in the later that this is actually going to reduce down and factor or factors will cancel in the numerator denominator. So negative 6 plus 6 cancels with each other. So you have the limit as h goes to 0 of 3h all over 2h all times 2 plus h. You can cancel those h's. And so we have the limit as h goes to 0 of 3 all over 2 times 2 plus h. So now when we plug in 0 wherever we see an h in here, notice that this will give us back a number. And so we get 3 all over 2 times 2 plus 0. Which is equal to 3/4. So this is the slope of our tangent line. Or another way to write this is f prime. And we looked at it when x was 1. So f prime of 1 is equal to 3/4. Okay, so that's the slope of our tangent line at x equals 1. Again, we had a point when x was 1, y ended up being, oh, is it negative 3/2? So we can use the point slope formula, y minus y sub 1 all over m times x minus x sub 1, or alternate form, or I just think this is so much faster and easier because it's already in the form that we want at the end. So if we plug in our y value, so y is negative 3/2 is equal to our slope. So our slope was 3/4 times x, and our x value was 1, is plus b. So we get negative 3/2 equals 3/4 plus b. Let's subtract 3/4 on both sides. I'm going to need a common denominator. So I have negative 6/4. I'm going to subtract 3/4 on both sides, so minus 3/4 equals b. Where b is equal to negative 9/4. So now we know b and we know our slope, so we know the equation of the tangent line. So y is equal to our slope, which we said was 3/4 times x plus b, and b was negative 9/4, so minus 9/4. Okay, so let's just kind of go, you guys can copy that down while I go to Desmos, and let's look at what we just did. So let's look at the graph of our normal function, f of x. Let's look at the equation of the line that we found for our secant line, going through that, and then let's look at what's happening, that equation of the tangent line at x equals 1. Let's see. Okay, so our first equation was -3 all over x plus 1. And then our second equation you guys remember y is equal to y is equal to, let me just write this down so I don't have to go back and forth. 3/4 x minus 9/4. And we saw y was equal to come on. Where's the first one? Y equals 1/4 minus 7/4 is 1/4 x minus. Okay, so it was 1/4 x minus 7/4. Okay, so we had found 2 points. We had found the point here when x was 1. Notice that we got -3/2, which is -1.5. We found this point here when x was 5. We found that our y value was -1/2 or -0.5. And then we found this equation of the line that passed through both of those 2 points. So that was the equation of the secant line. And now let's look at adding in the tangent line for a second. So our tangent line was y is equal to 3/4 x minus 9/4. So this was a line that had the slope exactly at x equals 1 of our function f of x at x equals 1. And we found this equation of the line that has that same slope and this point. So this right here is a more accurate, right, of what's going on at x equals 1 for the slope versus if I was looking at these 2 points to kind of estimate what the average was at this slope. It's not as good. Okay, so this is probably a good place to take a break. But I want to look at one that is a radical, and then we have to talk about a function is not always differentiable everywhere. And so looking at the cases where it's not differentiable, how can we find that? Looking at a graph, could we tell? And we can. So those will be things we'll look at when we come back after break. Sorry, I just want to pause the recording, not stop it. Okay, I know this recording is still being, we're just going to stop.